go live and wonderful. Welcome to today's materials and manufacturing seminar. So our speaker is someone whom I've known for many years, and you'll hear a formal introduction in just a moment. But so next week we don't yet have a speaker. We have a speaker for every week, but we'll find somebody for next week. And let's see. Repeat last week's announcement that if you are a first-year master's student interested in an RA, please contact myself or Brajendra Mishra. So with that, let me turn it over to Chinenye Chinwego, who's going to introduce our speaker.
Great. Thank you so much, Professor Powell. And thank you for joining us, Matt Earlam. Hello, everyone. It's an honor to introduce to you today Matt Earlam, a prominent figure in the metallurgical industry and the material science and engineering field. He has over 30 years of experience, and he's a graduate of Colorado School of Mines. He has previously worked in a number of companies, including the Dow Chemical industry. He was a principal process engineer in titanium metals, was a manager of the metal process development molecular minerals from 2011 to 2013. And he was also a manager in the metal processing engineering of Infineum and a materials process engineer. He's currently at the Argonne National Laboratory as a materials process engineer. His research interest spans from production of dysprosium ion alloy through electrolysis of molten fluoride salts, neodymium praseodymium metal production from a molten fluoride salt, and to magnesium recycling using molten salts, and production of rare earth magnesium alloys through electrolysis. And so with this, I'll turn the floor over to Matt Earlam for his presentation, and see you all at the Q&A session. Thank you.
This work? Can you see it?
Looks good.
Okay. See if I can get rid of this somehow. There. Okay, so what I'm going to talk today, one of the projects I actually have worked on in the past, after Infineum and before Argonne, I worked for a consulting company on lithium metal production. So this slide is about lithium metal production by electrolysis. Currently, Argonne is working on lithium metal production by electrolysis as well, but that's for a commercial client, so I'm not really allowed to discuss what we're doing for them, but give you a general overview of the way lithium metal is made now in the United States and around the world. So people are pretty familiar with lithium. They think about lithium ion batteries. That's a big use of lithium, but there's also a lot of use of lithium in other areas. There's use of it in alloys with aluminum. There's a lot of use of it in glass making. There's some small alloy use in magnesium. That alloy string is pretty small. There's chemical uses. Desiccants is a good one for drying air because lithium chloride is extremely hygroscopic, and it's easy to remove the water from lithium chloride solutions by heat and without a lot of hydrolysis. So it's useful as a desiccant. And then of course, there's some lithium salts used in pharmaceutical industry as well. If you look at where it comes from, there's basically two supplies, one of which is lithium brines, which are in the United States, Argentina, Bolivia, Chile, all over the world. There are lithium brines of various grades, and then there's spodumene ore. Spodumene ore was the original supply of lithium. There's a dike of spodumene minerals that runs along the Appalachians. So a lot of lithium companies in the United States are located in North Carolina. The reason they're located in North Carolina is because that's where the original ore bodies were found. And once that ore was played out, or these lithium brines were discovered in other places and more economical to exploit, they kept their factories in North Carolina, but they pretty much ceased their mining operations. So the brines can be evaporated by nature, but that doesn't get you to the concentrations you need to use to electrolyze. So there's a number of steps that have to go through, and we'll go through about these steps. And then we'll also talk a little bit about spodumene concentration. Spodumene is in the ore is maybe 8% of the ore body, and only a small fraction of the weight of that is actually lithium. So there's a lot of gangue that's involved with spodumene production of lithium, using spodumene for production of lithium. And so as a consequence, it's kind of lost its luster as it was, because the lithium brines are so much easier to access, although they are complicated in themselves. Here's just an example of where the lithium is used right now. Typically in the world, there's about 77,000 kilotons of lithium carbonate produced. Lithium carbonate is the mineral product or the chemical product that's traded in lithium mostly because it's a dry carbonate. It doesn't have waters of hydrations associated with it, unlike some other carbonate minerals. About 30% of lithium from lithium carbonate goes into making lithium metal for lithium metal uses, mostly in batteries. A good fraction, about 35%, goes in glass making, which is this purple section here. And then there's a lot of little other uses for aluminum smelting, greases, polymers, stuff like that. So most of the production actually is geared towards glass making and battery making, and the battery making is growing in leaps and bounds compared to glass making, which is probably pretty static in terms of tons per year. So let's talk about the brine route, because this is where most of the stuff is actually converted at this point. So the natural brines can be concentrated by solar evaporation to about 6% lithium as we use lithium as lithium chloride as a basis, just because that's the basis that they use to look at. So as the brine evaporates, the sodium chloride and calcium sulfate drop out of solution. And then you end up with a concentration that's a lithium magnesium chloride double salt, similar to carnallite, which is shown here. The potassium will also drop out as carnallite. Carnallite is what's used in submagnesium production, but that's important to understand because the Great Salt Lake has some supply of lithium in it. We'll go over that in a minute. And a company out in the Great Salt Lake, US Magnesium, has actually started to look at producing lithium chemicals from the brines in the Great Salt Lake. They've not made a tremendous amount of progress, but they have started looking at this as another mineral they can extract. I don't have any data on the lithium content of the Dead Sea, where also carnallite is produced to make magnesium. I imagine it's somewhat similar, that they do have some lithium values in that salt, but I don't know what they are. So as you reduce, most of the potassium and sodium are removed, and then you continue to evaporate, and you get to about 4.6% lithium chloride in a magnesium chloride, lithium chloride solution. Further evaporation gets you about 6.2%, and at this point you precipitate out the equivalent lithium carnallite, which is similar to the potassium carnallite that participated earlier. Then you react this with sodium carbonate, and the sodium carbonate will drop out lithium carbonate as a solid. As I said before, it doesn't have a lot of waters of hydration. It doesn't have any waters of hydration, actually. So it's pretty easy to separate. You can separate it by filtration and then crude drying just to produce the lithium carbonate. If you want to produce lithium chloride, which is what we have to do to make lithium metal, then we obviously just react lithium carbonate with hydrochloric acid, and we produce a lithium chloride, which then we can, if we control the chemistry right, make a very strong brine, so we don't have to remove a lot of water in the evaporation process. You can add sulfuric acid to produce a lithium sulfate. Some people use lithium sulfate in chemical use. And then, of course, there's some lithium nitrates as well. So you look at the natural brine compositions, you can see here in this column is ocean, which has very small amounts of lithium. And here I was wrong, there's the Dead Sea. The Dead Sea does not have a lot of lithium in it. Great Salt Lake has 3 times more than the Dead Sea. Bonneville, which is the other part of the Great Salt Lake, is actually bifurcated by a road. So they have one side, which is Great Salt Lake, and the other side is Bonneville. They're connected with water, but they actually separate them into 2 compartments because U.S. Magnesium has mineral rights to one section of the lake and not to the other. There's also lithium in the Salton Sea, which has been subject of investigation to try to remove. And there's a company now that's trying to remove lithium from the Salton Sea. It's been tried before. It's difficult hydrometallurgically because there's a lot of arsenic in the Salton Sea. Makes it difficult to separate and handle the byproduct arsenic, which is a problem. Silver Peak is a brine deposit in Nevada, which is used right now for exploitation. And then you look at the brine deposits in Chile, and they're just so much higher in lithium than any of these other sources. And you can see why that would attract mining companies in their interest to extract lithium, because there's a lot less water to remove per lithium weight than there is on these other solutions. And so all these brine processes really boil down to water management. I've got a lot of water to separate from the lithium. The less water I have to separate from the lithium, the more economical my process will be. Also notice there's some boron in these. Boron is a known killer of current deficiencies in electrowinning cells, molten salt ones. So we really have to get rid of this boron if we're going to do something electrolytically. Bromine, not so much. Chloride is obviously the counter ion for the cations in there. Magnesium, you'll see, is important, as well as sodium, because lithium has such a high decomposition potential. Any potassium or sodium that's excess to what we're trying to do will actually report to the cathode and contaminate our lithium, to the point at which you always have some potassium contamination in your lithium, and purification is required in some cases to remove the potassium from the lithium metal. I'll show you why that happens in a minute. So you look at the concentrated brines, we can get to situations where we're pretty high in lithium, 6%, and then magnesium and sodium, potassium follow along. Sulfates are minimized, and then we still have a significant fraction of boron that we're going to have to deal with. So further concentration by evaporation doesn't improve the magnesium to lithium ratio. Basically have to do a carbonate addition to get the lithium separated from the magnesium. The boron is removed by reaction with alcohol. And then the carbonate is produced by the reaction with sodium carbonate. It drops out lithium carbonate or the bicarbonate. The calcium and magnesium carbonates can be adjusted by controlling the pH at about 8.5. Control the carbonate ratio is necessary. As I say, crystals of lithium carbonate are produced. This is a ultra high purity, can be produced by ion exchange, and then we react it with HCl to produce a monohydrate. So the spodumene process is a bit different, and this is a bit more ancient actually. We take beta spodumene, which is a natural mineral that's found in the ore, and we heat it up. And when we do that, we convert it to alpha spodumene, a different phase of spodumene. There's a tremendous volume change in the crystal size when this occurs, and this allows us to fracture the mineral pretty easily because we go from a density of about 3.5 to about 2.5. So we have a massive change in density. So that changes the powder significantly to the point at which we can treat it with sulfuric acid and carbonate and separate the lithium sulfate solution from the rest of the minerals, which is basically calcium sulfate, silica, and alumina. And then once we get the lithium sulfate solution, then we can convert that with sodium carbonate back to lithium chloride, similar to what we would do with a brine, except in the brine, we just produce the carbonate directly. We don't have this lithium sulfate intermediate step. So let's look at electrowinning. So there is one plant in the United States that does electrowinning. It's in North Carolina. They use a potassium chloride, lithium chloride bath because lithium chloride is very hygroscopic and is a pretty high melter. Lithium metal melts at about 180 centigrade, so you don't really want to run a cell that's too hot, because in all these electrolytic processes, the further away you are from the melting point of the metal you're interested in, the less likely you have very good current yield, because you have higher solubilities of chlorine in the electrolyte, which causes recombination, and then that causes it to current yield to go down. These cells are small. In the electrolytic processes, you want to try to run in heat balance, meaning the Joule heat across the anode-cathode gap is what controls the amount of heat you're entering. You lose heat through the endothermic reaction and also products leaving, evaporation and conduction, and convection around the cell is another way that heat is lost. And then you also have a quenching effect because the way the gas is scrubbed. So in this process, lithium metal is very, very, very light. It's less dense than water, which is kind of interesting. It's about 0.5 gram per centimeter square. The bath density is about 1.6. So because it's so different in density, there's not a lot of protection of the salt film on top of metal if it's floating on top of the bath. And so the way that this is modified is that they add a mineral oil to the surface, and that floats on the electrolyte and protects the metal a little bit so that it doesn't oxidize so rapidly. The metal is collected by hand ladling, and this whole process takes place in a dry room. So you are operating a cell about 10,000 amps in a dry room, circulating air through the dry room all the time because you have to remove the chlorine gas, and then that dry air you've made then leaves with the exhaust. So you have a massive dryer in the dry room. This facility I visited in North Carolina, the desiccant dryer is about the size of a locomotive, just to dry the air that goes through the process. It's a tremendous amount of air has to go through the process because we have to remove the chlorine gas from the operators. And we want to remove chlorine gas as soon as possible to cut down on any recombination of the chlorine with the lithium. So as I said, they operate in a dry room. The dew point's kept at about -40 Fahrenheit. And the chlorine is evolved under a slight vacuum and under the cover of about 1/2 inch of water column suction. That's enough to move the chlorine away, but not so much that it sucks in so much air from the dry room that you just can't keep up with it. The cells are pretty small, so there's no real value in compressing the chlorine for sale, because you're not really generating a lot of chlorine compared to a chlor-alkali plant. So it's not done. What they actually do is they scrub the chlorine that comes off, so it's been diluted with air, with the sodium hydroxide to produce bleach. And then the bleach material, which is sodium hypochlorite solution, is sold for sale, is sold as a product. So there's no chlorine recycling in this process. And so unlike magnesium process with or titanium process where the chlorine is recycled to produce feed, in this process, since the brine is used and it's concentrated lithium chloride solids are used, there's no recycling of the chlorine, there's no value for it. Your electrolytic processes are in North America, your brine processes are in South America. So there's no connection between them in any way whatsoever, other than one's a customer of the other ones that's produced. And because of the chlorine gas and the temperatures involved, there's a lot of personal protective equipment that's necessary for the operators. Heat resistant material, respirators, things like that, that really add to the ergonomic burden of the operators when they actually do this job. So this is what the cell looks like in cross section. This is a good representation of a cell. So you have a number of features. You have this graphite anode, which is somewhere between 2 and 4 inches in diameter. You have a steel cathode, which is here. You have electrolyte all inside, and then you have a way to get the lithium out. Here I've shown it as a duct. Some cells, they have a overflow similar to a sodium cell. Some cells, they use a hand ladling situation. They have salt addition. This is manually done by adding salt in powder form to the cell. And then you actually have an air addition that allows you to pull the chlorine air mixture off at a pretty low concentration of chlorine, like somewhere less than 10%. Still deadly to a person, but a lot less damaging to equipment because you've quenched the chlorine considerably by this air addition that you pulled in this way. So these cells are small compared to electrolytic processes of like aluminum or magnesium. And there's not a lot of tons compared to aluminum or magnesium. So there's not been a lot of research on how to make these cells. These cells seem to be children of a design that was started in the 50s and slowly evolved over time to be better. How much better and how much further they can go is a subject of debate. We'll talk about that in a little bit. But there's a couple of things that are going on in terms of modeling the cell to try to figure out how to optimize the cell. And the first of which is to look, when I say gap, I'm talking about the distance between the anode and the cathode. And you have to remember these are both round. So it's a cathode is round and the anode is round. And so as you get further out, the resistance goes up differently. It goes up as a logarithmic function instead of just a straight function because of the fact that these two surfaces are round. So what you have, and you also have chlorine evolved here on the anode as a gas, and so it's coming off and out. And then metals evolved on these plates, comes up and is swept out either this way or into another pool over here where it can be harvested. So you have an effect, right? Because of the gas bubble void fraction in that annular space, you have a change in resistance. So as the gap gets smaller, obviously we can short it, and so we have zero resistance. Resistance will go up as the gap goes up a little bit, and there's more volume. The volume of the bubbles increase inside compared to the volume inside the gap, and so you get to a point where the resistance starts to go up, and then it starts to come back down as the void fraction of the bubbles gets smaller in terms of the space inside the annular space. And then eventually it'll start to go up again because you're way far away from the cathode. And so there's an optimum resistance somewhere in here that minimizes the gap, the optimum gap. And this number is somewhere between 1 and 3 inches, probably about 2 inches, maybe a little tighter, depending on the load. The other thing that happens is you have recombination, obviously, you have chlorine reacting with the metal. And so the closer the gap is, the more contact you have with chlorine and the metal. And so your recombination rates are really high, which means your current yields up here are very small. They get better down here. So you want to increase the gap for current yield, but you want to not make it too large because then the resistance starts to go up and your energy consumption starts to go up. Also, your heat production starts to go up, and so you have to manage those two things in conjunction with each other. And then the other thing that happens is that you have an anode gas lift pump. So as the chlorine bubbles evolve here, it pulls electrolyte up and over, which is important because it helps you sweep the metal off the cathode through collection. But if you get too close, your pump rate basically stops because you don't have enough electrolyte to pump. And then as you get the gap too far, your pump becomes ineffective because you're not getting a lot of movement of electrolyte compared to the amount of electrolyte that's in there. So there's an optimum gap in terms of pump rate that's somewhere in between 1 and 3 inches in this scenario. So people have tried to scale this process, and there's a couple of techniques that have been used. One of which is, and I'll show you here some data from it, mathematical modeling system using flow models, typical flow models in these phase systems. The problem that they have with them is it's difficult to model the gas lift action accurately because that's not been very well studied. And then the model is really good at measuring the resistance. The gas lift action affects the void fraction to a little bit, so that needs some more work, but is pretty good. And it can model the three phases, the lithium phase as well, because there's a big density difference between lithium and the salt. So those are pretty easy to model. Water models is which was what we worked on about 2 years ago. There's really good similitude between water and air and chlorine and salt. So you can do a pretty good physical model. The bubble shapes and sizes and rate of rise between chlorine and salt and water and air are about the same, because the Morton numbers used to describe that flow are very similar. But it's really difficult to model the lithium phase because of the fact that the density difference is so high between the salt and the metal, almost 1 gram per cc. It's very difficult to find a model for lithium that will represent lithium properly. So there's some issues with modeling by water, and then there's some issues by modeling by computer. I think together they help each other out in terms of figuring out the best solution. But in the end, you still have to run a cell. And the cells aren't really very expensive because they're pretty small. So you have to balance the cost of how much these models cost versus how much actually it costs to run the cell. Because you could change the anode cathode gap in a cell pretty easily, because here's an example. Here's the example of the similitude between water and chlorine. You can see the Morton numbers, which is defined as viscosity, density difference between the gas and the liquid, density of the liquid, and the interfacial tension are very similar between water and air and chlorine and salt. So you can actually use them interchangeably pretty well. Hard to come up with a model for metal though in a water-air system. Very difficult to do that because the density difference is so high. It's hard to come up with something that's really a really good model. And the interfacial tension is a little different as well. So if you look at the current cell designs, what they basically are 4 anode cathode pairs in a tub, and each one is got a cathode in the center, so it's center ring, and then an anode in each one, and they put current through it, and they generate lithium metal that floats on this surface. Hopefully they've constructed the gas lift action so that it kind of gets directed towards the front, so the operator can collect the lithium metal in a ladle, which is what he does. We operate at this kind of operating point. So you can see here's the eutectic diagram, here's the phase diagram, potassium, lithium chloride. We operate at about this point, a little beyond the eutectic, kind of a little more lithium rich. But you can see there's a big melting point reduction from the lithium salt, which is at 607 down to 352. So you really want to operate here. You start to get too far this way, you start producing potassium metal ends up in your lithium. And so that has to be removed in some applications. Luckily, the vapor pressures are pretty different. And so you can do a distillation to remove some of the potassium from the lithium if you have to. So if you look at it, the anode current densities are about 1 amp per centimeter squared, typical for a molten salt system. The eutectic is 352. The sodium must be reduced to less than 1% in the lithium chloride, less than 1/10%, because at 1/10% sodium chloride in the brine, or the lithium chloride will produce a 1% sodium alloy, which is not what we want. So we really have to control this potassium and lithium. You can see that because potassium and sodium reduces a lower decomposition voltage than lithium, that it's important to get it out. Potassium is a lot closer to lithium, so you have a little less of that switchover problem. So here's what a cell actually looks like in terms of sizes. So you have here in this example, which is a German cell, not the ones in North Carolina. The anode is about 1 foot in diameter, and then the cathode is about 35 inches in diameter. So the gap is about 2 inches. And then the total bath around this cell was 700, it was 70 centimeters, so pretty big. They operate at about 6 to 9 volts. The current yields are about 90%, which is pretty good because this lithium is very reactive with everything. And so getting that kind of current yield is pretty good, actually. So that's basically what they look like. I don't have any really good pictures of them. I wasn't able to take pictures of the ones in North Carolina, so I can't show what they look like. So the people in the University of London have actually done some modeling of this process, and what they looked at was like changing the anode cathode gap. Here it is in millimeters, and then the anode radius, here it is in millimeters, and then look at the lithium production rate in terms of moles per hour, which is their use, but actually it kind of correlates to kilowatt hours per kilogram, which is what you really want to be interested in. So what they found is if you can minimize the gap to about 80 or so millimeters and keep the anode smaller rather than bigger, then your maximum production rate curve is about here and then about here. So that was kind of interesting. Here it is in a table form. So they also adjusted the anode the height of the anode and cathode pairs in their model. That's important because of the gas lift action that takes place, and also if they run a constant load, that changes the current density on the anode to a smaller current density, which means that you have less gas production per square centimeter. But you can see what they end up with is a situation where the kilowatt hours per kilogram of lithium is about 28. So to get you some examples, magnesium runs about 13 kilowatt hours per kilogram of magnesium, and aluminum even less. So you can see, because of the decomposition potential is so high in lithium, that it really affects the kilowatt hours per kilogram of lithium metal made. And some of the examples where they really increased the gap, you can see they got to some pretty high energy consumption numbers. These numbers are important, and I didn't go through this exercise completely with you all, but this number is important because we need to figure out how much heat's being put in the system by the anode cathode gap joule heating versus how much we can remove through convection and conduction around the cell. Because we have to run the cell isothermally. We don't want to have to heat them extensively. So we want to run them off the joule heat that's produced. So we have the joule heat that's added, and then we have heat that's removed. And a lot of heat is removed actually from the decomposition of the lithium chloride. That is an endothermic reaction. So that removes a lot of heat. And then there's convection and conduction that removes a lot of heat. And then there's sweeping of the chlorine that removes some heat. And then the metal production removes some heat. But most of your heat loss is going to be in the endothermic reaction and the convection and conduction around the cell. So by improving the brine quality and therefore the lithium carbonate quantity, we can actually produce lithium at pretty high purities, up to like 30 ppm sodium down to 40 ppm potassium. These other transition metals less than 10 ppm. So their big contaminants are sodium, potassium, calcium. All of these come from the brine. So that's, and then the magnesium, but they've been able to produce that as well. So that was kind of interesting that they've been able to do that. So what do you do with this stuff? Well, to make lithium ion batteries, you actually have to make a lithium foil and laminate it to a copper backer. In some cases, they just use graphite, but in the applications that I'm involved in, we're using a copper backer. So lithium is very soft and very difficult to handle. So you have to roll it. And they typically have to roll this material in a dry room because lithium is so reactive with air. They've been able to get down to less than 30 microns in some cases, rolling to make laminations for batteries. Their battery manufacturer's goal is to try to get this number as small as possible, but there's yield losses that start to occur when they get much smaller than that. That's basically all I have on lithium. It wasn't a full hour, but hope you liked it.
Thank you very much, Matt, for that insightful presentation on lithium production by electrolysis. At this point, do we have any questions from anyone?
Wow, no questions.
Matt, this is Brijendra.
Yeah.
I have a question. There was some talk about Afghanistan having a large source of lithium carbonate. What happened to that? The countries you listed as the sources for lithium brine, I didn't see that. So is that still?
They if they mine it there, that's not a big. They may have a big supply in an ore body, but they're not mining it at this point.
I see.
So the
Okay.
supplies I've looked at are actually where they're mining it, not where there is resources. It is kind of interesting. The USGS has estimated that there's only about 150 years supply of lithium in the world right now at current consumption rates. And not all of it is exploitable. So that has to be taken into consideration. There is a limited amount of lithium. It's difficult to recycle from a battery, as you can tell. If the battery is 30 microns of lithium metal in a big battery, it's really tough to get it out. And it's so reactive that it's not going to be lithium metal by the time you get it out. So that's an interesting dilemma in terms of batteries. It makes people interested in looking at other battery compositions with time because of the abundance of lithium. So say compared to magnesium, which is like cubic miles of brine in the ocean that have 1,300 parts per million magnesium in them. So a lot of magnesium available in ocean brine compared to lithium supply. I did see there's an ore deposit, a brine deposit in Arkansas, which is they're trying to exploit. But to show you an example, the brine in Arkansas has been known about since at least the 1970s. So 50 years, and it's still not exploited for lithium. Somebody is trying to do it now using a modified ion exchange system to remove the lithium. We'll see how well they go with that. It's tough. I mean, there's been at least 3 companies in the Salton Sea trying to get lithium out of it, and they all go bankrupt eventually. So it's a tough business to be in.
So for now, the problem is, for now, most of the lithium comes from the other source, the ore that's mined.
No, most of it comes from brines in Chile.
Right, but it's all about like getting the right concentration in the brine.
Yeah, well, same. In spodumene, you don't have to concentrate the water, but you end up with a tremendous amount of waste, a solid waste, right? Because you probably end up with maybe 50 tons of solid waste for every ton of lithium metal produced, because the mineral isn't very concentrated with lithium and it's just fused in the ore body. So. And a lot of energy too, right? Because I have to heat it up to crack it, and then I have to do these leaching steps.
Okay, Professor Powell, you have a question?
Sure. Glad to defer to others. So first, you'll be glad to see that 39 out of 40 participants got the main sources of lithium correct. So that's great. A question, there are Chinese producers that are making a lot of lithium. Do you know much about how they make it? And is there significant difference between the practice in different countries?
I don't think there's significant difference in how they make it. There's production of lithium metal in Russia as well, at Irkutsk. Lithium production in Russia is a state-owned industry. It's owned because they use it in nuclear weapons. Because of that, it's state-owned. But they use a similar technology. There's been not a lot of investment in the cell design. The other cell design that was used is the down cell, which is what's used for sodium production. That was patented in 1924, and I can't see that they've made any real improvements since then. So there's areas for improvement in this process, but it really has to generate a big enough market to generate enough revenue to put resources in to exploit it, right? Because if they're not making a lot of money in terms of flow, then it's tough to put any money into fixing it unless you have the the government involved and we use a national lab or something to do that. But right now, that's not our focus. We're not, as a national lab, we're not into that. We're kind of into Tierra levels 2 to 3, not 6 or 10, right? So if we got to 6 or 10, then we might be able to do some help, but right now that's not our interest. You'll see there's some papers on plating lithium for organic solutions, which is interesting, but there's a lot of issues with that as well. So.
I was wondering, given the huge differences in boiling points of a lot of the elements that make up the brine, is there any ability to skip some steps in the refinement process by just, I mean, I imagine if it made sense thermodynamically, somebody would have done it already, but is there any combination of just dumping a lot of heat in to boil off individual elements at a time, or centrifuging some sort of mixture to avoid some of the waste steps?
I think from what I understand, the mines are at a pretty high altitude. So water management is very hard because they're up in these areas that have very little water. So just getting materials to the mine site is difficult. I would think you're right, though, that there would be some kind of reflux boiler system like they used to use in chlor-alkali to separate the salts by boiling, and then using a heated centrifuge to separate the salts out, because that's how it used to be done in chlor-alkali. When they used to use asbestos diaphragms, they would boil the catholite and separate out the caustic soda from the brine, sodium chloride, which would drop out of solution. They could separate it with a centrifuge, and they did that typically by boiling. But from my understanding, that these mine sites are very hard to access in terms of equipment because they're very high up, very hard to get water to and from. And I think they also, because of that, they don't have a lot of fuel either. So they're so dry and so high up that solar evaporation is obviously the way to go. Even US Magnesium, which gets snow because they're in Utah, uses solar evaporation to get their mag chloride concentration up in the Salt Lake to a point where they can start to chemically treat it, versus somebody like Dow that used to use caustic soda to drop it out of seawater, because Dow had an excess of caustic soda sometimes, and also had lime that they could use to raise the pH to the point you could drop out magnesium hydroxide from seawater. You can't drop out lithium hydroxide from any brine. It's miscible across this entire range. So you end up having to use sodium carbonate to drop it out. There's no chlor-alkali production in the high parts of Chile either. So there's no caustic soda up there because there's no chlorine production up there, and there's no power. Very hard to get power up there to run a chlor-alkali plant as well.
Okay, thank you so much. That's interesting.
Any other, Professor Powell, do you have a question?
Sure, I always have questions, and I like to defer to students, but so when I look at this cell design and compare it to, say, an aluminum production cell, in aluminum production, the graphite anode is consumable, it gets consumed. But you said that here you produce chlorine and not any carbon compound. And I also, in an aluminum cell, they make sure that the metal is on the bottom, where here the metal is on the top. Can you talk about why the chlorine doesn't react with the carbon anode or with the produced metal?
It does react with the produced metal to some degree. That's why the current yield is only 90%.
I see.
It doesn't react with the chlorine anode. The biggest problem you're going to have with the chlorine anode is any air ingression, because it'll react with the anode and burn it. So
Okay.
the anode loses weight over time. And the other thing that would happen, that does happen, I'm sure, is that if there's any water in the lithium chloride, then that will react with the anode and consume it as well. And that water will decompose to produce CO2 or CO on the anode, and then get into the lithium as a hydrogen involved on that side. So controlling the water is important in the dry feed. It's got to be really dry, otherwise you're going to have that reaction. The other thing that would happen is you'd flash off HCl when it hit the salt. Water
Okay.
hits the salt, it flash off some HCl as well from a hydrolysis reaction.
Okay. Yeah, I can understand there's some reaction between the chlorine and the metal, but if you lose only 10% of the we call it the current yield with that reaction, is there something else getting in the way of that reaction, or are there it seems like it could be a pretty violent reaction if to really get going with
Well,
it.
I think that what happens is that the salt itself has a solubility for chlorine.
Oh, okay.
So you end up with chlorine dissolved in, especially in potassium chloride, it has a pretty high solubility for chlorine.
Hmm.
So you don't, it's
Okay.
not a gas metal reaction, it's a diffused chlorine in the salt reaction with the lithium that causes it to be consumed.
I see.
Because you're right, if it was gas metal, it would be basically a lithium fire, right? It's basically what you would have. So a metal
Okay.
fire, you don't have a metal fire, you just have a reaction with the dissolved chlorine in the salt and the lithium metal.
All right. Yeah, that's what I was wondering. I would expect a metal fire in this in this atmosphere. So, but
Yeah, well, that's
okay.
why I think they dilute it so much with air, is to cut down on the
I see.
metal chlorine fire that would occur by metal floating on the surface and being reacted with the anode gas. So they want to cut it down as much as they can. So there's a balance between how much refrigerated air they can use versus how much they're going to lose in terms of burning.
I see. Okay. Thanks.
They could do a different design where they use the gas lift pump to force the lithium under a surface, like the old Dow magnesium cells did, and then collect it under salt. But they don't do that. And I don't know why they don't do that, but that's not what they would do. That would be, if I was in that business again, that would be what I would look at was, is there a way we can use this gas lift pump to pump the solution with the lithium droplets in it under the surface and then collect it underneath so it doesn't have any chance to recombine with floating gas? Then I might be able to make a stronger chlorine, which mean I would have to buy less refrigerated air to run the cell, which would help my costs, but you'd have to build a cell to do that. And most of these situations is like, well, we have these cells running, what cell are you going to take off? And I might not be able to make metal when you're doing that. So I have to make a cell somewhere else. And it starts to get into how much money do I want to save on this versus how much am I really generating? So it's a constant dilemma with these people in terms of how much resources they have and how they want to spend it.
Do we have any more questions?
I suppose one more quick one, please. In terms of the geometries of the cells, where if you're going with, I mean, advantage is obviously that it's radially symmetrical, so it helps with your modeling efforts. But have you looked into going with thinner, almost like plates for your cathodes and anodes, so that you'd have much, like you could have, if there is that optimal gap, instead of, would you be able to basically set up just plates of your cathode and anode at
you
that?
would. And so like the Alcan Mark IV cell, which is an aluminum cell, uses plates, anode cathode plates. And so does the magnesium cells that US Magnesium uses plates instead of round. The advantage of round is that that's how it's extruded. So the graphite maker makes it round. They can also make it block. So that's not a big issue. The big advantage to round that you have, the biggest advantage to round that I have, besides it being one-dimensional versus two-dimensional, which actually is not really that big an advantage because we can all model two-dimensional now. It's not like you have to do everything in one dimension, right? So that's not the big issue. The big issue is just sealing it. It's a lot easier to seal something that's round than something that's square, because trying to get a gasket to turn a 90 degrees corner and maintain integrity when you seal it at room temperature, now you're heating it at 400 C, you tend to lose the gap. So you tend to have air leaks around the gap. And if you have air leaks around the gap, then you have air burn around the gap, and then you lose an anode not from chlorine consumption, but just air consumption, hitting the anode at temperature, and then it causes it to wear. And eventually you have to replace it because mechanically it becomes unstable and might fall. So you have to pull it out and put a new one in. So the only advantage around is modeling for one, but I think the biggest advantage is sealing. And there's ways to accommodate the sealing. You just round the corners of the anode instead of making it exactly 90 degrees and work with it that way, which is what we did what we did at TimeIt when I was there. We rounded the corners that were blocked anodes because those anodes were square, were rectangular in cross section. So.
That's really interesting. That's actually not an angle I even would have considered. So thank you. I was just thinking, I mean, with flat plates, you'd be able to get a lot more cathode anode pairs in close proximity. And also you could just pump a crazy amount of flow through them, which would also help to spread out almost the bubble flow. You could even probably pump so fast that the bubbles are going down.
Yeah, you could. You can do that with round too. Yeah, you could do that. It starts to become how easy it is for the operator to operate the cell, right? So the other thing you have to think about is that probably doesn't occur to you, but because it occurred to us only after the fact, was like, well, if it's square and I want to change an anode out and I don't really want to turn the cell off when I'm doing that, the magnetic field that's generated by the current that's going through the clamp will want me to rotate the anode in a direction that I don't want it to go. So if it's anode round, I don't have that issue because there's no corner. So it's easier to insert an anode that's round in a magnetic field than one that is not. So the alternative to that is turn all the cells off when you change an anode. Well, that cuts into your production a bit. So you have to balance that. I mean, that was a thing we did at Dow is we converted some cells to rectangular anodes from round ones, but then we ran into this magnetic field issue where the clamps became magnetized, and then they would want to rotate in the field in a direction we didn't want them to, and so we had to have all this extra mechanical restraints to stop them doing that while we inserted them. So the body itself becomes magnetized where it's cold enough to accept that. So that's another issue that you have to think about is when you get to really high currents, it becomes even more important. But these currents, you're starting to, you're generating a magnetic field. You've got a current going through a conductor, so you're generating a magnetic field.
You are correct. That's definitely not an angle I'd thought about. I was just thinking like eventually you could set up some sort of almost bar feeder type thing where you're constantly, as you're consuming the anode, you're just running a
well, the anode doesn't get consumed. It only gets consumed by air burn. It doesn't get consumed by chemical action. So air leaks are the detriment, right? Because it burns where it wears is at the free surface of the salt where the anode is hottest and where air is present. So that's where it burns. And so if it loses enough weight at that joint, it becomes mechanically unstable and then it falls in and then you have to fish it out, which is possible. It's not fun, but it's done all the time in magnesium cells. It's a pretty laborious thing to do. And it wastes the graphite because the graphite, these anodes graphites, they cost about $21 a kilogram. So I don't want to be burning them if I don't have to. So.
Okay, thank you. Those are all very interesting points that I definitely had not considered. So thank you.
So do we have any more questions? Anyone?
It doesn't look like it. So I think it's just about 1 o'clock here, just about 12 where Matt is. So thanks very much. We appreciate your
Can
seminar.
I ask one more question if it's
Sure.
okay?
Yeah,
Sorry
right
for
ahead.
waiting. Yeah. Recently, I heard there's enough lithium in the US to hypothetically fuel the entire lithium transition to lithium-ion batteries. However, based on what you've said, the amount of lithium isn't really the problem. It's purifying it down to a point where we can use it, correct?
And the cost in doing that.
Okay, so how do you feel about the whole, do we have enough of a lithium industry to like convert to lithium-ion batteries?
You know, in this kind of business, the desire to do it gets you a long way. So if there's political will to do that and enough people in the country are interested in doing that, yeah, I think you could do that. I think I would point out that the total global supply of lithium is only 150 years at current consumption. So converting to lithium batteries might get you somewhere, but you're gonna have to convert to something else later. Because even at 150 years consumption, some of those deposits are not exploitable. So we can't just convert to lithium batteries and think we're done. We have to keep looking at other ways of getting power because lithium won't last forever.
But can't you recycle lithium batteries?
No. Very difficult to recycle. The value in the lithium batteries is the cobalt and the lithium. And lithium getting out, as it gets thinner and thinner, becomes more and more difficult to get out.
Won't come out as a metal, but people.
So you can recover it as a chemical, but there's a lot of other chemicals that come with it. So
that's true.
And they do recycle them. I mean, it's, you know, I shouldn't say no, you can't recycle them. Yeah, they can recycle them. How much it costs to get them out and how much lithium recover versus how much was in, it's not clear to me. You're not going to get it all back.
Okay. Well, that brings up a suggestion for speaker of Eric Rotz, who was a postdoc here working with Yan Wang and founded a company that has raised a lot of money for a battery recycling company, battery recycling pilot plant.
Yeah, there's a
So,
couple of them around. So
yeah,
it's going. And it'll shake out. Somebody will come out with the best solution, and then that'll be the one that people will go with.
Makes sense.
But
Well.
you know, I don't know how long that'll take, and I think there's batteries coming beyond lithium batteries that are going to be just as economical as the lithium ones are. People aren't stopping on battery research. It's a big emphasis for everyone. So
Makes sense. Great. Okay. It seems like there's a good amount of interest in this topic. I'll certainly invite Eric and see if there are others we can bring in. So. All right. Well, I need to run. If there are other questions, be glad to turn over the host position. Any more questions? Yeah. If not, I'll stop the recording and the live stream, but keep this going. So, all right, do that quickly.